Hello students, today we are going to start the next topic, that is differential equations. Now we all are already familiar with equations of the type x squared minus 3x plus 3 equal to 0, or those involving trigonometric functions like sin x plus cos x equal to 0, or simply a linear equation like x plus y plus is equal to 7. Now let us consider equations of the kind x dy by dx plus y equal to 0, or another one as 2 d2y over dx2 plus dy by dx whole cube equal to 0. Now we notice that though the first three equations they involve dependent variable, which is sin x or cos x or y, or independent variable, that is x and some constants only. The fourth and the fifth equations, they involve, along with the dependent variable which is y and the independent variable which is x, they also involve derivatives of various orders. Like here you have derivative dy by dx, here we have the second order derivative and third power of the first order derivative. Now such equations which involve the derivatives of the dependent variable along with the dependent variable and the independent variable are called as differential equations. Now we have the definition as the same, that is equation involving derivatives of the dependent variable with respect to the independent variable is called a differential equation. Now if the differential equation involves only one independent variable, as the case which we are going to consider this year, then it is called as an ordinary differential equation, else it is a partial differential equation, which is beyond the scope of our syllabus. Okay, so in this year we'll be doing only ordinary differential equations, which we will be addressing as a differential equation. Now mostly we prefer to write the derivatives as, instead of dy by dx, d2y by dx2, d3y over by dx3, we write y dash, y double dash, y triple dash. And obviously as the order increases, instead of putting dashes, we prefer using numbers, like yn would be used for the nth order derivative and so on. Similarly, even for smaller derivatives, we use y1 for first derivative, y2 for second derivative and so on. Now we come to see something which is called as order of a differential equation. Now as we have seen, differential equation involves derivatives of various orders. Now order of a differential equation is the order of the highest order derivative present in that differential equation. Like for example, if the derivative differential equation is dy by dx equal to e raised by x, the highest order derivative is of the first order, and so it's of order 1. This equation d2y by dx2 plus y equal to 0 will be of order 2, as a second order derivative is the highest order derivative present. In this case we have a third order derivative and a second order derivative also. So the order of this differential equation would be 3. Now we come to the next thing, which is degree of a differential equation. Now to study the degree of differential equations, the given differential equation must be a polynomial in the derivatives, that is y dash, y double dash and y triple dash and so on. Like for example, consider three differential equations. One is d3y over dy3 plus 2 d2y by dx2 whole square minus dy by dx plus y equal to 0 clearly is a polynomial in the derivatives, various derivatives. Here dy by dx whole square plus dy by dx minus sine squared y is equal to 0 is also a polynomial in the derivatives, though it is not a polynomial in y because of the presence of sin y term. Okay, but whatever the case may be, since it is a polynomial in derivatives, in both these cases degree is defined. Whereas if we consider the differential equation this dy by dx plus sine dy by dx equal to 0, this is not a polynomial in the derivative because of the presence of trigonometric function of a derivative, and so in such a case the degree is not defined, and thus we have this rule that the degree of a differential equation is defined only if it is a polynomial equation in the derivatives, and then it is defined as the highest power, which is taken as a positive integral index, highest power of the highest order derivative involved in a differential equation. Okay, so by in that manner this differential equation is of degree 1, because though the power of one of the derivatives is 2, but the highest order term present here is of order 3, and this has power 1, and so the degree of this differential equation will be 1, whereas over here dy by dx is the highest order term and its degree is 2. The highest order term, the power highest power which is present here of this term is 2, and so the degree of this differential equation would be 2, whereas in this case because of the presence of trigonometric function of a derivative, it's not a polynomial in the derivatives, and so degree is not defined. And we come to a rule which we have to remember, that if any differential equation has terms involving trigonometric functions of a derivative or logarithm of a derivative or exponential function of a derivative, then we say that degree is not defined for such a differential equation. Another point to be noted is that order and degree, if defined, are always positive integers. This you have to keep in mind. Now with this you can do the exercise 9.1 and check out for how to identify the degree and order. Now the next thing which we have to see is the general. Now that we have a differential equation in our hand, now the next natural thing is finding its solution. Now there are two types of solutions of a differential equation. One is called the general solution and the other one is called as the particular solution. Now just as an ordinary equation, the solution means a value which satisfies that equation. Same way for a differential equation also, the solution means the value of y which satisfies the differential equation. Value of y means the dependent variable which satisfies the differential equations. So as I've already mentioned, there are two types of solutions of a differential equation. One is the general solution and the other one is the particular solution. Now in case of a general solution, we mean an expression of y, which is a dependent variable, as a function of x, which is the independent variable, having as many arbitrary constants as the order of the differential equation. Means if in the solution of a differential equation we have the number of arbitrary constants is equal to the number of equal to the order of the differential equation, we say it's a general solution. Whereas in the solution, if the number of arbitrary constants is less than that of the order of the differential equation, or there is no arbitrary constant at all, in such a case we call it a particular solution. Now here one point is to be noted, that in a particular solution, though there is no arbitrary constant, it doesn't mean that there won't be any constant. We'll have some fixed constant in the solution. The only thing is an arbitrary constant is missing or is less in number as compared to the order of the differential equation. Okay, now one important point which we have to remember is that the general solution is a process of removal of derivatives and involves exactly n arbitrary constants corresponding to the differential equation of order n. Likewise, the differential equation, if you have to form a differential equation corresponding to a curve, It will involve the removal of the arbitrary constants and addition of derivatives in the process. And so we get a differential equation of order n corresponding to a curve having n arbitrary constants. Okay. So with this, I have introduced you all to the concept of differential equations, its order and degree, and the types of solutions which we have for a differential equation. Thank you.